Now I'm sure you're all wondering, okay, we know how to calculate the volumes of a solid of rotation. How do we find its surface area? If I had something like y equals f of x, and I rotate it around the x-axis, then what is just let's say I take an arc length. I just take sum of its length from here to here. Let's say it so happens to be from A to B, and I rotate it around the x-axis. It will come like this, and it will form sort of a sheet, sort of a, I don't know, toilet paper tube that's been squeezed in the middle or something like that. A hollow thing. You can put your hand through it. But what is the surface area of that? Well, again, as with always, we chop it up into a great number of little bits, and we add up all of those bits separately, and we're going to use an integral to add them separately. But let's take one of the pieces. Let's go from here to here. Let's say that's some point x. And as we've seen before, the little bit of x right there is going to, the little bit of x right there, how about I get rid of the whole picture? Well, just to give them some more room. We have one little interval, there's x on it, and we look at this little piece here. Now we saw during the arc length that the length of that is approximately the square root of 1 plus the derivative of f squared dx. And when we rotate that around, we are going to get a cylinder. A cylinder whose radius is given by the function. If that's x, the radius is f of x. And remember that the cylinder area is, what was it, 2 pi r h, which in this case is 2 pi f of x square root of 1 plus f prime of x squared dx. And if we're going to add those all up, we use an integral. And so the surface area formula is the integral from a to b. Might as well put that 2 pi out front. F of x times the square root of 1 plus f prime of x squared dx. And just to be obnoxious, if we wanted to take that curve y equals f of x and rotate it around some different horizontal axis, say y equals c, from A to B, then when we take a little piece at x, so let's see, it's going to come this distance here, will go the same distance there, and then it kind of curves in a little bit, so we get sort of this smaller cylinder curves in the middle of the cylinder. If we take an interval x and we look at just this piece, again, that arc length is going to be exactly the same. It's still going to be the square root of 1 plus f prime of x squared dx. But now our radius here, in this case, is going to be f of x minus c. And if our axis had been way down here, it would still be f of x minus c, because that would make you're subtracting a negative number that's adding just as we would want. If the c is up top, our radius to that area is going to be c minus f of x. So you could either switch it around to c minus f of x or use absolute values. Here the surface area will be 2 pi, the integral from a to b of, oh man, do I even have enough room here? Oof. It will be 2 pi, the integral from a to b, f of x minus c times the square root of 1 plus the derivative of f squared dx. And in fact, this formula, you can use absolute values if you want to take care of the cases of vertical axes, the horizontal axes that are above your area. But this actually rules out this formula, because if this was rotating around the x-axis, also known as y equals 0, and it would just put a 0 in there. So it is the same formula. Here is your formula. People are having trouble plugging into formulas, but what can I do? Learn these formulas. I'll do a couple examples in subsequent videos.